In this problem, we are given the following circuit diagram right here. We need to use the node voltage method to find V0 in the circuit below. This is perfect because our V0 is located right here in the middle of this node. So we're going to be using this node as our primary node. Step 1, we defined our nodes. The equations right here are for this example specifically. I've only linked it to reference 2. And it's also provided in the notes in the description. Now we're moving on to step 2. Where we have node 1, which is our node 1 in red. We're going to look at the left side of our node. Well, from the left side, we can see that we are going to have some current going in to our node like this. It's going over the 10 ohm resistor. To calculate this current, we're going to take our V0 and subtract it from the 10 volts coming into it. And this is going to all happen over the 10 ohm resistor. Next, we are going to be looking at the next current, and it's going down this way. So we're going to have a plus V0 over our 40 ohm resistor. The reason why it's also going down is because we have our plus minus, which indicates the direction of our voltage. To our right, going this way, we can see what the direction is. And this voltage right here, this is going to be our second voltage. We'll call it V2, and it's going from minus to plus. Normally it goes from plus to minus like this. However, this diagram is going from plus to minus, which means it's going up like this, and it's actually going this way. So it's not going to the right, it's going to the left. It's going into our node. That means when we have our plus V1 over the resistance right here, it's actually going to be a V1 minus a negative 20I delta. Normally it would just be like V1 minus V2 as it is right here. However, since our current is actually going into our node, we're going to have a minus up here. It's kind of why the reason why when we look at the second node, the current going into here is negative right here. It's kind of the same reason. And this is happening over the 20 ohm resistor, and this is all equal to 0. Normally we would need to look for our V2. However, it's not unknown here. What's unknown is our I delta, so we need to actually find our I delta. I'll write it like this here. Normally for our I delta, it would be like V2 minus V1 over the resistance that it's between. However, this is slightly different since it's an I delta, not an I naught. Looking at our I delta, I'll draw this in red. It starts right here, and we can see that it's a parallel split between this direction and this direction. Since it's in parallel, at this node right here, that means the currents at which it splits for will have to add up. So the current going over our 10 ohm resistor and the current going over our 30 ohm resistor are going to have to eventually add to equal our original I naught. So we'll say that I naught is equal to the current over our 30 ohm resistor plus the current over our 10 ohm resistor. Now we're going to plug some things in. For our current over the 30 ohm resistor, it is going like this. And we can see that it's actually going the opposite direction of the voltage, because our voltage is going, as we recall, this way, but it's also, some of it is going this way. And we can see that these are in different directions, and since they're in different directions, we're going to have a minus. So we're going to have I naught is equal to our initial voltage, which is 10 volts, minus our negative 20 I delta. So we'll have a minus negative 20 I delta, and that's basically our V2, and this is all happening over the 30 ohm resistor. From here we can add, and then our next part going over the I10, we're going to have our initial source voltage 10 volts minus the V0, because this V0 would be going this way and our source voltage is actually just going out. We're going back into the node, and this is all happening over the 10 ohm resistor. From here, we're just going to simplify this, and this is all happening over the 10 ohm resistor. From here, we're just going to simplify and add like terms. First thing I'm going to do is multiply everything in here by 40 ohms to get rid of the denominator, and I'm going to do the same thing down here, except this is going to be 30 ohms. Again, this is just to get rid of the denominator and then combine like terms. I did make a mistake, I just noticed this while doing this, but this is a V0, and this V1 should also be a V0. I also added a voltage right here and voltage right here. That way we can get the correct units. This I delta right here should also just be I delta amps because the current is measured in amps. Notice that as well as I was going through this. And after doing all of this, we're going to get that our two equations are this right here and this right here. We have two unknowns still, but this is a little bit easier. Now we can solve for one. I'm going to look at our second equation right here, and I'm going to multiply everything by 4. That way we can get a 40i delta v as we have up here, and just plug everything in our right side into here. So after I multiply everything by 4, we're going to get that, and then I'm just going to plug it straight into our first equation. So we're going to have 7 v naught plus 160 volts minus 120 v naught, and this is equal to 40 volts. I made a slight mistake also. I just realized that this should be a 3 v naught, not a 30 v naught. So that means this is also just a 3 v naught right here instead of 30. And that means instead of being 120 right here, we're just going to have a 12 v naught. So this is just going to be a 12 v naught. After we have everything corrected now, we can start adding like terms. So we're going to have a negative 5 v naught. We're going to subtract 160 volts from both sides, and we're going to get that this is equal to a negative 120 volts. If we plug this into a calculator, we're going to get that our v naught is equal to 24 volts. And this is the answer for this problem.